Hello everyone. Today we'll be looking at challenging problems from the SAT Math Geometry sections. These are problems that you could expect to be on the latter end of your digital SAT Math modules. Now these problems are conceptually difficult, so understanding approaches to solve these kinds of problems will better prepare you for SAT Geometry, which is a subject I know many people find confusing and stressful. I encourage you to pause the video and try some of the problems throughout this video before looking at the solution, just to get a feel for how this video is going to go. And without further ado, let's get started. The curve y equals x squared over 2 and the line y equals x over 2 intersect at the origin and at the point AB as shown in the figure. What's the value of b? So we have to set the equations of the curves equal to each other. So I can write x squared over 2 is equal to x over 2. When I subtract x over 2 from both sides, I get x squared minus x over 2 is equal to 0. This just means x squared minus x equals 0. And if we solve this quadratic by factoring, we get our solutions are x equals 0 and 1. Now we're not looking for the solution that passes through the origin. They already tell us that. They want the other point, where x equals 1 and y equals x squared over 2 and x over 2. Now in both cases, y was equal to 1/2, and that's what we want. That's what we want, the y-coordinate of that point, so our answer is C. Now in the figure above, AB equals 6 and BC equals 8. What's the area of triangle ABC? Now there's a very niche formula. To find the area of a triangle given two sides and the angle between them. In this case, we have two sides, 6 and 8, and we have the angle between them, which is 60 degrees. And that formula is 1/2 AB sine of theta. Theta is the angle between the two. So I can, write this formula out. Sine of 60 is √3 over 2. I can cancel out 2 and 2 and make this 8 and 2, 2. Right? This is like doing 8 divided by 4. So our answer would be 12 √3. And we'd be done. But I want to show you how I'd solve this problem if you didn't know such a niche formula. Now I see the angle 60 degrees, and I immediately think about special triangles. Special right triangles, specifically. Now, our triangle here doesn't look like a right triangle, so I'd probably try to make one. Let's see, how would I make one? Well, I have this 60 degrees here. I need a right angle. How would I make a right angle? Oh, yeah. I could draw the altitude from A to side BC, and I get my right triangle that way. So that means this angle is 30 degrees. So we've created a 30, 60, 90 special triangle right here. Right? And by our special triangle rules for 30, 60, 90 right triangles, our shortest side, which is the hypotenuse divided by 2, is opposite the 30-degree angle, so that means the side I just marked is 3. And then our altitude is just the shortest side times √3, which is 3 √3. Okay, now we have our altitude, 3 √3, and the side it's perpendicular to, 8. In other words, we have our base and our height. And we know how to find the area of a triangle given the base and its height. It's just BH over 2. So that's what I have here. 3 √3 times 8 divided by 2, that's just 12 √3, and we're done. Now, number 3, we have this problem. In the figure above, 3 is less than or equal to A is less than or equal to 5, and 6 is less than or equal to B is less than or equal to 8. Which of the following represents all possible values of C? So we need to find the minimum of C and the maximum of C. The minimum of C occurs if B is the longest side. Right? If B is the longest side, then the sum of the other two sides has to be bigger than B automatically by the triangle inequality. Right? And we want to minimize C, so we want to minimize the difference between A and B. So if I pick A closer and closer to 5 and B closer and closer to 6, well then C has to get closer and closer to 1 at its minimum, but it always has to be bigger than 1. Correct? Now if we assume that C is the longest side, then A plus B has to be greater than C. So now we have to maximize A plus B. In order to do that, we can bring A closer and closer to 5 and B closer and closer to 8. That means C will get closer and closer to 13, but actually never reach it. So C has to be less than 13 at its maximum. So in conclusion, our final inequality for C is C has to be between 1 and 13. And that's answer choice D. Alright, let's move on to the next problem. Line L goes through points P and Q whose coordinates are 0, 1, and B, 0, respectively. For which of the following values of B is the slope of the line L greater than a half? Now, let me take my 2 points 0, 1 and B0 here. Right? I'm going to take B0 as x1, y1. And then the second point here is x2, y2. Now our slope formula is y2 minus y1 over x2 minus x1. Well, let's just plug it in. So we get y2 minus y1, which is 1 over 0. And x2 minus x1, which is 0 minus b. And this is just negative 1 over b. Right? So, for which of the following values of b is the slope of the line greater than negative 1/2? Right? So what we're doing with the slope, right? Our slope is negative 1 over b. Right? We have our different values of b. And with our different values of b, we're going to take the negative reciprocal of each to get our slope. So if b was 1/2, our slope would be negative 2. That's no good. It's not greater than 1/2. Negative 1/2, it's less. Now if it was 1, it would be negative 1. That's also less than 1/2. If a b was 3/2, it'd be negative. Our slope would be negative 2/3. That's also smaller than a half. Negative a half, I should say. If it was 5/3, our slope would be negative 3/5, which is negative 6 over 10, right? But our line L's boundary, our boundary given in the problem, is negative 5/10, so it's still smaller. The only answer choice remaining is E, so that's probably right, but let's check. Our slope would be negative 2 over 5 if we take the negative reciprocal, and that's negative 4 over 10, which is bigger than negative a half, so E is our answer. Okay, next problem. In the figure above, AB equals 6. Okay, immediately let's mark that. AB equals 6 and BC equals 8. Perfect. Okay, what is the length of segment BD? Right, okay. So first I'm going to solve for AC, since BD is perpendicular to AC. Right? I'm going to get AC squared is equal to 8 squared plus 6 squared. This is equal to 64 plus 36, right? AC squared. AC squared is equal to 100, so AC equals 10, right? And we know BD is perpendicular to AC. So we can calculate the area of the triangle using BD and AC. The area of the triangle is BD times AC. We know what AC is. It's just 10 divided by 2. And that's equal to the area of the triangle. Well, we know the area of the triangle is just 8 times 6 divided by 2. Right? We can calculate it another way. Right? So I'm just going to cancel out the 2's. And we get, let's see, I'm going to write it up here. BD times 10 is equal to 8 times 6, which is 48. BD is what is it? It's 48 over 10. correct? Which is equal to 24 divided by 5. And that's our answer. Now let's just make sure, right? The area of the triangle is 8 times 6 divided by 2, which is 24. 10 times 24 over 5, right? And then we have to divide that by 2. Now these are the same thing, so our answer is correct. Alright, if 4 distinct lines lie in a plane, and exactly 2 of them are parallel, what is the least possible number of points of intersection of the lines? Okay, so I'm going to draw 2 parallel lines. So that's our line A. I'll make this as close as possible. And it'll pass. That's our line B. If 4 distinct lines lie in a plane, what is the least possible number of points of intersection at the line of the lines? Right? Can it be 2? Now, if you draw one line, right, you intersect both lines twice, because for any pair of given lines, they can either intersect once or every time, right? And we're looking for the least possible number of intersections. So if we're given just one more line, we can cut it down to 2 intersections because these lines are parallel. Now if we're given 2 more lines of intersections, now each line will intersect both of the parallel lines twice. So that's 4 intersections. But we want to minimize it, right? So what we can do is we can have both lines go like this, right? We can have both lines intersect one of the 2 parallel lines at different points and then share a common intersection point on the second parallel line. And then they'll never meet again. So we can minimize our intersection points to 3. And that's our answer for that question. The perimeter of a particular equilateral triangle is numerically equal to the area of that triangle. What's the perimeter of the triangle? Okay, so we know our equilateral triangles are have angles of 60 degrees. I should probably draw that bigger. Hold on. Let me do that. Right, I'm going to draw a bigger triangle. Okay, let's just pretend that's equilateral. So each angle is 60 degrees, right? And each side has length s. Now, in order to find the area of this triangle, I'm going to split it in half, right? I'm going to split it in half. Now, this angle right here will be 30 degrees. And this angle right here will also be 30 degrees. So that means this side S, not this side S. This side, by our special triangle rules, will be S over 2. And so will this side. Right? And then the altitude will be just the shorter side multiplied by root 3. So now we can calculate the area of the triangle. We know the altitude is S root 3 divided by 2, and our base has length s. And we have to divide this by 2 to get the area of a triangle. So the area of our triangle in terms of s is s squared root 3 divided by 4. Right? Now what do they tell us in the problem? The perimeter of a particular equilateral triangle is numerically equal to the area of the triangle. So our area, s squared root 3 divided by 4, is equal to the perimeter of the triangle, which is 3s. Now let me switch to a different color and solve this problem. So, first of all, we can divide both sides by s, right? So we get s root 3 over 4 is equal to 3. And then we get s is equal to 3 times 4 divided by root 3, which is 12 over root 3, which is 4 root 3, right? So the perimeter, 3s, will just be equal to 12 root 3. And let's check our work. If I substitute s equals 4 root 3 into this equation, I get 4 root 3 squared times root 3 divided by 4, which is equal to 48 root 3 divided by 4, which is equal to 12 root 3, which is the triangle's perimeter. So we know we have the right answer. Alright, let's keep moving. In the figure above, a square is inscribed in a circle. If the area of the square is 36, what is the perimeter of the shaded region? Okay, now what I'd like to do is draw the diagonals of the square in order to split up this diagram into useful sections that we can use to solve this problem. Alright, if we know the area of the square is 36, we automatically know that the side length is 6. Now, if you didn't know already, the diagonals of a square intersect at 90-degree angles, right? They all intersect at 90-degree angles. So then that means that this region over here, I should probably do this in a different color. Here, just a second. Let's do this. So then this region right here that I've highlighted in blue is a quarter circle of the circle that the square is inscribed in, right? The only problem is, in order to find this arc length, right, we want to find this arc length. But in order to do that, we need to find the radius of the circle. Now the radius of the circle is just the diagonal length divided by 2. And, you know, from our special triangle rules, we can easily find that the diagonal length is 6 times the square root of 2, which means that the radius of the circle is 3 root 2. Right? So our arc length will just be the ratio of the inscribed angle to the number of, degrees in a circle, 90 degrees over 360 degrees, times the circumference of the circle, which is 2 pi r, or 6 root 2 times pi. Right? Now this is just equal to 6 root 2 pi, all divided by 4. This is 3 root 2 pi divided by 2. I'm going to rewrite that. And we have to add 6 to it to find the perimeter. So our perimeter will be 6 plus 3 root 2 over 2 pi, and that's answer choice A. Now, let's keep moving. Alright, number 9. In the figure above, AC equals 7 and AB equals BC. Alright. AB equals BC. What is the smallest possible integer value of AB? Now, they asked for the smallest possible integer value, which means we're probably going to have to use an inequality here to determine a bound for AB. Right? And since we have a triangle here, let's just use the triangle inequality. And the triangle inequality tells us that the sum of the lengths of any two sides has to be greater than the length of the third side. Strictly greater, I might add. So AB plus BC has to be greater than or equal to AC in this case. Right? Now, AB is equal to BC, so AB plus BC is just 2AB. And AC is just 7. So 2AB has to be greater than or equal to 7. Now remember that AB has to be an integer, right? So that means 2AB is an even integer that has to be bigger than 7. So essentially what we're doing is we're trying to find the smallest even integer greater than 7, right? And the smallest even integer greater than 7 is 8. So we know for our smallest integer value of AB, 2AB has to equal 8. So that means AB must equal 4. Right? And that's our answer. Let's move on to question number 10 here. In the figure above, two line segments in the xy plane form a right triangle with the x-axis. What is the value of A? Okay. Looks like we're going to be using some distance formulas. Well, this is going to be fun. Okay. We have a right triangle. Let me reconstruct it up top. Our hypotenuse has length 10. Right? Let's say this is our origin, 0, 0. And this is our ending point, 10, 0. Or actually, that's not realistic. But just assume it is, even though by the diagram it isn't. So then that means this point is 2A, right? So we have to calculate the distance, or rather the length of each segment of the right triangle. I did that horribly. Hold on. Okay, so first let's find the length of this segment here. By the distance formula, this is just A squared plus 4, right? A minus 0 squared is just A squared, and then 2 minus 0 all squared is just 4. So that length is A squared plus 4. Right? And then now we have this length here. Let me erase the shoddy diagram right here so I have more space to write. Okay. So in this case, we have to find the length of this segment right here. By the distance formula, this is 10 minus 2 squared plus 0 minus A squared. Right, and this is just equal to 8 squared plus A squared. So now I know the lengths of both line segments that are in the figure in terms of A. Now I can just apply the Pythagorean theorem on them. You know, the sum of the squares of both sides should equal the square of the third side, 10. So in reality, 8 squared plus 4, right, which is the first side squared, plus 8 squared plus A squared has to equal 10 squared, which is 100. Alright, now I'm going to collect like terms. 2A squared plus 68 equals 100. 2A squared is equal to 32. A squared equals 16. And that means A is equal to 4. And that's our answer. Okay, moving on to question number 11. The perimeter of square ABCD is X, and the perimeter of isosceles triangle EFG is Y. If AB is equal to EF is equal to FG, right? Which of the following must be true? Okay. So I'm going to draw both figures. Right. That was a badly drawn side. Let me just do that again. So we have A, B, C, D. Now if the perimeter of this square is X, each side has length X by 4. And that's just common knowledge. And then we have the perimeter of isosceles triangle EFG is Y. So this is our isosceles triangle EFG. I'm going to pretend EF and EG are the equal sides. Or no, they tell us two equal sides. Never mind. EF equals FG. Right? Equals AB. So if AB is x divided by 4, then so are EF and FG. So I'm going to write that down in the figure right here. Right? And then they ask us, if that's true, which of the following must be true? And we have a bunch of inequalities that we need to solve. Right. So I'm going to start with our triangle EFG, because we can apply the triangle inequality and get some type of bounds that we could work with. Now, first of all, we know that the perimeter of this triangle is y. So 2 times x plus x over 4 plus EG is y. Right? So we know EG is equal to y minus x over 2. Now, I'm going to apply the triangle inequality, right? Leaving side EG as the third side, so we can get some clear bounds for it, right? So we have EF plus FG has to be greater than EG. EF plus FG is just x over 2. And this is greater than or equal to EG, which is y minus x over 2. Now, adding x over 2 to both sides, we get x is greater than y. Right? X is greater than y. But this isn't really helping us with the problem. So let's see what we can do here. Okay? We found a lower bound, or rather a ceiling for y. Let's see if we can find a minimum for y. Right? So I'm going to place EF or FG on one of the other sides of the triangle inequality. So I'm going to say, let's see, I'm going to do EF plus EG is greater than FG. EF plus EG is greater than FG. X over 4 plus EG, which is y minus x over 2, is greater than FG, which is x over 4. Right? So I can subtract, or rather cancel out, x over 4 from both sides. And I get y minus x over 2 is greater than 0, which means y is greater than x over 2. Right? So we've established a minimum and a maximum for y. So by doing so, we can construct the following compound inequality. We can say x over 2 is less than y, which is less than x. Right? And this is answer choice C. And we're done. Now moving on to the next question. Question 12. In the xy plane, the lines y equals 2x minus 1 and y equals x plus c intersect at point P, okay? And c is a positive number. Portions of these lines are shown in the figure above. Okay, if the value of c is between 1 and 2, what is one possible value for the x-coordinate of P? So first of all, let's set up an algebraic equation that helps us determine the intersection point of these two lines. Let's set the equations of the lines equal to each other. So we can set 2x minus 1 equal to x plus c, right? And we're going to solve for x. So I can subtract x from both sides, and I can say x is equal to c plus 1, right? That's what I get. And they tell us, what do they tell us? They tell us that, let's see. They tell us that c is between 1 and 2. So c is between 1 and 2. So that means this is true about c. Let's add 1 to both sides of this inequality. We get 2 is less than c plus 1, which is less than 3. Now c plus 1 is just x, so we can substitute. So we know that 2 is less than x, which is less than 3. So x is between 2 and 3, right? So I'm just going to pick a random value between 2 and 3 and call it a day. I'm just going to pick 2.5. Keep it simple. You guys can pick anything crazy or whatever. But yeah, that'll be my answer. You can submit any answer you want as long as x is between 2 and 3. So don't submit like pi, because that's wrong. If you want to be like nerdy with it, you could write e, right? You can even write some limit that's between 2 and 3, right? Yeah, but yeah, that's the gist of the question, and it looks like we're done for the geometry section of this. So thank you guys for watching, and be sure to share this with anyone that might find it useful in their SAT preparation, especially for geometry. And I'll catch you in the next video, where we will uncover some more hard problems from other sections and other topics that are covered in the SAT math section. So thank you, everyone. Don't forget to subscribe and